So we're going to be talking about sequences today. We're going to be talking about brand new content, stuff you've never seen before, because we are moving on from the second third of the course. You had your second midterm, and we will be grading that imminently, and then should have that back to you relatively soon. Thank you all for your participation with what's been happening with the fire alarm and so on and so forth, because that was it's been a stressful few days for me for sure. But we made it through, most of us. Worth noting that still not everybody has taken the exam, so don't go around openly discussing what was on it. Okay, all right. But sequences are kind of cool, and we'll see why. I won't spoil it yet. All right. So here's your code. All right. So sequences are going to be a different kind of data structure, and they're going to admit a kind of interesting cost model. We're going to see how we can sort of think about doing certain operations in a cooler way, and how we can do it in a faster way. Also worth noting that we are now in the third. I believe I will send out a poll tonight to a blue team who won the second third, unfortunately. I would have rigged it if I could. All right, cool. So fundamental data structures anyways. I previously said to you something like there are there are only a few fundamental data structures in computer science we haven't really looked at so far in this course. But you know, you have your arrays, and what an array is it's just a container that has a fixed number of elements where each element can be mutated. So I can have an element where I have 2 in the second index or the third entry, and then I can later, go and erase it and revise it with 3, and so on and so forth. Okay, and if I wanted a longer array, I'd have to make a new array. All right, my array has a very fixed length, which is fundamentally different than the list, because we know that lists you can cons onto the front for very cheap, and you just kind of still have the same list, but plus the first thing on the front. Okay, so we haven't really talked about arrays, but that changes today, because some of you will be like, oh, you can't do O of 1 constant time indexing in a functional language. Think again. All right. So that's what we'll be doing today. So arrays are sort of characterized by their ability to do this constant time indexing. And usually we think about arrays in the context of lower level languages that are closer to C, more imperative features, right? Because mutability kind of comes in the package for an array. Okay, but we can actually still do that kind of thing here in a functional setting, because constant time access is cool, but let's skip the mutability. So we're going to be introducing sequences, which are like arrays, but they're immutable arrays. We still maintain the property that you should not be able to change an array without creating a new array. Okay, all right. So sequences are an immutable data structure that have a fixed size where every element inside has the same type in the same respect as a list does. And we can index in constant time to any given element at any position. And we also have the same property that if I did an out of bounds access, I'd get like an exception or something. Okay, if I tried to index into this with 9,000, that would be kind of silly, and the compiler will yell at me, or not the compiler, but the runtime will yell at me. And our key is that we're going to be able to make it immutable. If we change an element of this sequence, we're going to make a brand new sequence. And that might seem like kind of cost prohibitive to you, right? It's kind of silly, but we're going to find that actually for most operations we're interested in doing, this will still maintain good performance for certain applications, whereas being slower for others. There will be advantages and disadvantages to working with sequences. There's a reason why we didn't start with it at first, okay? But I want you to know that this is very much a trade-off, okay? We use lists for some things and sequences for some other things, okay? And for the purposes of sequences, think about them as arrays, just arrays that you cannot mutate, okay? At least underlyingly. When you have to reason about how much it costs or what the runtime model is, think about them sort of as arrays, okay? All right. But there's a good question, which are how are sequences actually implemented? Where can you see the code for that? And the answer is it's a secret. And I'm not joking. Like for the purposes of this class, we are literally not going to show you any of the underlying code that underlies sequences, because it's a secret. And in particular, what it is it's an abstract type. We're going to be using the module system in this case. This is an application of modules where we're not going to know what the underlying type really is. A sequence is an abstract type that, conceptually looks like an array, but we can't really do anything with under the hood. That means that there are certain things we lose. We can't pattern match. We can't interact with sequences in any way that isn't in the sequence library, the module that I'm going to show you next. Okay? And we have a very large sequences library that's linked online on our 150 website, and also it'll be in the next few slides. So if you're ever interested in what functions are there, we're going to run through some of them in this lecture, but also you can go find it online, okay? But the key thing to take away here is that sequences are an abstract type. You have no idea what's going on behind the interface, but that's a good thing. All right. So this is our sequence signature. A sequence is a signature which is implemented by a particular library we're giving you. But there's a type alpha T, which is the type of sequences that store elements of type alpha. You have an exception range, which might be raised if you try to do something like an out of bounds access. But we have certain operations. We can construct a sequence. We can construct the empty sequence. We can construct a singleton. We can do some other things too. We can turn a list into a sequence, and I'll talk about this tabulate thing in a second. But beyond that, we also have a bunch of other destructors and modifier methods, such as these ones. So as I promised, we have nth. So I'm going to point out a few that are interesting. But we have nth, which lets you take a sequence and index into it in constant time. We have length. We can turn it into a list. We can check for quality. We can check if a sequence is empty. And we can do some simple operations on it too, like reversing a sequence, appending two sequences, so on and so forth. Okay, so like you should read this and feel pretty comforted because we're home, because this is basically what we can already do on lists, plus or minus a few things. So all of the things that we can normally do on a list are still pretty accessible to sequences. It's just that they're going to have different cost bounds. Nothing that we can do with the lists cannot be done with, or nothing we can do with sequences cannot be done with lists, and vice versa. But the cost will be different for certain operations, and that's what the focus is here. And then finally, we have a few more. We have like a bunch of hops here. We have filter and map and reduce, and this is really small text, so don't worry about it. But honestly, like there's still more. I cut out some of them. So refer to the sequence library for more. Yeah. We'll get to explaining what reduce is first, and then we'll talk about it. Yeah. Reduce is something new that you haven't seen before, but yes. That's probably the most interesting one on that page, I think. And there's a few other things. So check the sequences library if you're ever confused. But this is what we're working with. Pretty much just the same sort of containers, same thing as lists. Okay. All right. That's a lot. I had to describe to you what some of these did, but there's no description. Thankfully, online on the sequences library, there is a description of each function and its runtime costs. So if you're doing your homework and you don't know what something costs, you have to actually go back to the sequences reference on the 150 site and then reference that, okay? And I already said this, but the main thing that we get from sequences is they are very parallel. They are very parallel friendly. Lists are not, okay? It is impossible for me to write a function on a list that goes and visits every element and has better than O of n span, right? Does that make sense to everyone? Like if I want to do things in parallel, I can't. If I have a list, if I have x cons x's, I have to look at x before I look at x's, right? And so on and so forth. So sequences offer us this constant time access, which means that I can do everything individually on certain elements in the sequence at the same time. If I have n processors, I can do it on all n elements of the sequence simultaneously. That's the main thing that we get out of sequences, okay? Sequences are for parallel operations. Lists are for pretty much everything else. All right. And I'll tell you, for instance, we can do seq.map f within constant time if we know that f is a constant time function. Okay, so that's one thing that we can do. All right. Okay, and I already told you that we can do constant time access for sequences, which you should know is different than O of I we usually have to access the ith element. Because remember, I think someone actually asked us about this on Piazza or something. But if you want to do list.nth, it's implemented exactly how you think it is. Like you have the n, and you have an x cons x's, and then you decrement n by 1, and then you go to x's, and you recurse. And then when you're 0, I'm not going to write the function out, but you get the idea, right? No magic. Sequences are a little magic. Because they're like arrays, you can do this constant time indexing, but only a little bit. Oh, wow, okay, I had that. Yeah, so this is how you'd implement nth, but O of n work, O of n span, or O of I rather, right? So sequences, we're going to be able to do length in constant time, as well as doing all the other parallel friendly operations. It's worth noting that length in constant time is like not necessarily something that comes straight out of it being parallel friendly. Like that's just a fact of sequences. We can do length fast. Whereas length on a list is again O of n. Okay. That's just something worth remembering. Okay. There are advantages to sequences. I said there are also disadvantages. It turns out the same advantage of sequences is also its disadvantage. For working with lists, what do I do? I case on a list, nil or cons, right? I parse it. I look at exactly what it is. But a sequence is an abstract type. I can't do that. So to write this code, to write something that checks whether it's empty or otherwise, cons, and then does 1 or 2, for a sequence, I'd have to write this. This should look very familiar to you if you remember lecture 4. I case on the length of the sequence. If it's 0, I do the 1 thing. This is bothering me. Oops. Do the 1 thing, and otherwise I let x and x's be the nth at 0, and then I drop the first and I get the tail. Yeah. No, this is exhaustive. There's only 1 and 2 here. 3 time permitting would be we don't case on the length at all. There's a different way to do this, but the point stands that like this is the most obvious way to do it. The canonical way to do it is slightly different. I'll show you if we have time at the end of the lecture. But yeah, we don't have to do this, but my point is like you're tempted to do this. Like you can't pattern match at all. So we're gonna work on that, and we'll try to do a little bit better. Okay. Yeah. Oh yeah. I need to mention this is disgusting. Okay. This is disgusting. Let's try to do better. Let's do better. All right. Cool. Okay, so the other disadvantage being that they're designed with parallelism in mind, meaning that certain sequential operations are really friggin' slow. That means, for instance, if I wanted to do x cons x's to an x's I'm already holding, that's constant time, I told you. We're familiar with that. But to do cons on a sequence, if I want to do this, the equivalent of that, I have to make a brand new gosh darn sequence. So this is an O of n cost to cons, which is pretty hefty, okay? That means if you want to do a sequence of consing, you really are better off using a list instead of a sequence. Sequences are good when a priori you know exactly how long the sequence needs to be, okay? So yeah, so cons is expensive. Yeah, you need to make a brand new sequence. Is there a question on this? I hear your confusion, not your disappointment, but maybe both. Okay, I'm disappointed too. So this is what we're going to be working with here, okay? Sequences for parallel operations, lists for sequential. Cons is expensive. That's all you need to know from this section. And usually when we're working with sequences, we're going to be using a particular kind of syntax. So if I wanted to denote, this sequence that visually, pictorially, you denote like this, I would use this notation in math, where we use these angle brackets. Okay, so this is just how we choose to denote them in math, because it's kind of a pain, because otherwise we don't really know how to write it out in text. And then, for instance, we might write that seq.map f on this sequence right here has this cost where I maximize my x over all things in the sequence. The work of that, that should actually be the span, sorry, has the span of the maximum here. So the maximum cost to do this map is the maximum cost of any given f to any given element, right? This should be span. And then we would result in this sequence. So we're kind of mixing code and math here because we'll use this for a specification, okay? But before I can really show you how we use sequences, I got to tell you about some of the more fundamental operations that we use in sequences. And before I do that, I need to tell you about how to think about it. So we're going to talk about cost graphs. Okay, any questions on this first part, on sequences as a whole or this idea of sequences? Before we move on to cost graphs, which are cool and fun. All right, sounds good. I'm tired. I had to proctor the exam this morning. Okay, so we use cost graphs to kind of visually think about what a sequence is doing, what some operations are doing. Cost graphs are not exclusive to sequences. It's that they are really helpful for thinking about it. So a cost graph is sort of going to be similar to the same task dependency graphs I showed you earlier. It's going to illustrate the sequential dependencies and the parallel dependencies between certain operations. Okay, it'll tell us where we can do parallelism. So, for instance, here are the 3 key things you need to know about sequences. And I'm not going to draw it on the board, I guess, because it's right there. But I can compose these cost graphs with certain primitives. I have sequential composition, and I have parallel composition. And also, as my base case, I have nodes that denote the computation of something. Okay, so we use this node to denote the computation of the function f on some argument. Okay, it's not relevant to this example. So for instance, if I wanted to say that I have some costs where my cost is the cost of this graph and then sequentially doing this, that's the one I would use. Or if I wanted to say that my cost was the maximum among this cost and this cost, then I would use parallel composition, right? Sort of the similar thing as in a task dependency graph when we say this, this, this. And maybe we have some weights on the edges. In this case, we don't have weights on our edges. We just have edges that denote, that get us to nodes that do, okay? So we are saying that cost graphs are inductively defined by these three constructs. Just by repeating these three things over and over again, we can get every cost graph ever, okay? And analysis of these cost graphs is exactly how we're going to be thinking about the cost here. It's going to play into this lecture again, that think about things in terms of a picture. Cost has a picture, all right? So another thing worth noting, that cost graphs, I haven't put the arrows on it, but they implicitly all go from top to bottom, okay? I was too lazy to put the arrows on there. So we'll view them as directed going down, and every graph has a source and a sink. The source of this guy is the source of this guy. The sink of this guy, or rather, okay. The source of this entire thing is the source of the graph 2. And the sink of this entire thing is the sink of graph 1. And then the source and sink of this are just these two blue dots. And the source and sink of this guy are just that node itself. This is worth noting because when we put graphs together, their sources and their sinks are where they line up. So if I put, if I had this, where this is the sink of one, and this, where this is a source of another, the way that we do the sequential operation thing is that we take this sink and the source, and we just put them together, okay? So that's why the only reason why we have that notion here, okay? All right, any questions on the basics of cost graphs before we get into examples? Cool. All right, so I already told you this, but it's also worth noting there's this term called fork and join, fork join parallelism. It's a big thing at CMU. But the idea is simply that when you see a cost graph that looks like this, I go out, I do something, and I go back in. We call this like a fork join diagram. We fork here. We fork into two branching paths that might be done by two different processors, for instance, and then we join here. And this is pretty much how real-life parallelism works too. Sometimes you need to synchronize for two operations to finish. So this is where that synchronization happens. We wait until one of these is done, or rather both of these are done, and then we combine. Okay? All right. So I can mix and match them. As I said, we can put together these diagrams, these base diagrams, and produce every graph ever. So for instance, if I wanted a cost graph of 1 plus 2 quantity times 3 plus 4 quantity, this is what it would look like. I start at my source. Okay, I have to have a source. I have to start at the blue dot, basically. Okay, and then what happens? I know that I can do both of these in parallel. Well, what's the cost graph of both of these individually? What's the cost graph of 1 plus 2? Well, 1 plus 2 is just the operation plus. I don't really have to do anything else. There's no operation here, no operation here. I just have values. So this guy is plus, the purple node of plus, and so is that guy because that's 3 plus 4, right? But then once I'm done with that, I have to collect these results. I can't do this asterisk, this times, until I'm done with both of these. So I lead in with an edge to my asterisk node where I perform the multiplication. And that's where I join, right? I fork to go and look at each of these left-hand side and right-hand side, and then I join when I get the results, okay? Fork join parallelism, all right? And then note that also each of these has a constant time cost. So if I wanted to, I could also replace the computation nodes by what I call a cost node, which is where I annotate it with the work and span. So if I wanted to do that here, like look at this, we have plus, plus, and times. You could replace it by an equivalent cost graph, where now instead of plus, plus, and times, because I don't really care about the specific computation, I care about how much it costed. So I get 3 nodes where each one is constant work, constant span, because addition and multiplication are constant work and constant span, okay? If you're ACE, I don't want to hear it. All right. So now we can very easily see that if I take the work of this graph, which is the area, this is constant. And if I take the span of this graph, it's again constant. Okay. So I say that I would say that like reasoning about cost graphs, the way you should do it is you write out the one that has the computation nodes, replace it with cost nodes, and then sum. Either the area for the work or the depth for the span. Okay. This is a recurring theme. Remember that area is the work and then depth is the span. All right, cool. Area of the graph. Area as in like the sum of everything. I'm using area to denote like the sum at every node. Yeah, sorry. At least that's like conceptually how I think. Okay, fair enough. Cool. So yeah, so I guess I went into more detail about it here, but that's exactly what I just said. If I wanted to have something like an O of n operation in work, but an O of n span also. This is actually just like, you could think of this as basically syntactic sugar, honestly, for something which looks like this. O of n many blue dots. This is an O of n work, right? Because you have to march on and you sum all of the blue dots and you get n of them. But the span is also O of n because I need to go through all of them to reach the bottom, okay? So this would be the cost node associated to this little like computation subgraph or cost graph, okay, I should say. All right. So it's like worth noting that like, you don't need these computation nodes. It's just like better in terms of like your reasoning because you kind of get the point that like this is what it is, right? It's just a linked list basically, okay? But for the cost graph. So it's worth noting that this is kind of like a translation into the cost node diagram. We can do the same thing for the parallel case. So it's technically true that for fork join parallelism, you always have exactly two things. You have a left and a right, right? So if I wanted to, I could draw out something like, let's go left. And then this guy's going to go left and right again. And this guy's going to go left and right. And what do you know? It looks like a linked list, actually. And then maybe they, all eventually join back. Or this would even be not even work because you'd have to join back like with two. And then you join this back again. So you say like this. And then you join this back eventually as well. Right? Do you see what I'm doing here? I'm kind of saying like this is a parallel thing where the right-hand side can be parallel and that right-hand side can be parallel. But the thing is like, if you think about it, everything here can just be done in parallel. And eventually they'll join and it'll be like all of them coming together and that's not too big of a cost. So we prefer to write something like this. What you see on the board right now is the desugared version of this, or the rather the sugared version of this, right? Instead of drawing this out, like gross dependency thing out, I'm going to write, let's just assume it can be n-ary. The forking could be for any arbitrary number of graphs. Yeah. Yeah, I suppose I actually mean this. Yeah, I know. I guess I do actually mean this. Which is only when I was thinking of the case. So if in the case where you have a binary operator, like you do need to wait for both of those values. But I was actually in the case where you have like a tuple of like n-ary things, and yeah, this would actually be the true picture. In which case we could safely do this kind of like, or actually, yeah. So I guess actually let's just take it as a primitive that we can do this kind of n-ary splitting in general. And get rid of the binary case. I think you can rederive with the binary. Like I don't think you ever need to have strictly binary. But let's take this as a primitive. Good point. I'll get that true for that. I didn't think terribly hard about that. That was in the previous slides as well, the binary case. But yes, okay. But yeah, assuming that we have this not n-ary binary case, or assuming we have the n-ary binary case, this is just n many parallel composed graphs. So we do them all in parallel and we join eventually. And then we can also say that this is the same as this node, where we have O of n work because I have to visit every node, and then O of one span because I join them all together in one step, right? Rather, my height is one basically. Okay, so that's how we think of it if each of these graphs is constant. This is not the case if each of these graphs were to be like O of n squared. Does everyone see that? Like it's constant depth in terms of the graph, but each graph might itself be very large. Okay, that's worth noting here. Okay, so only if each of these are constant cost nodes. But now we can think in terms of the green instead of like desugaring to all of these giant graphs. Yeah. And that's pretty much everything about cost graphs. We're just going to apply this knowledge for the rest of the lecture. Okay. It's conceptually interesting to think about these, but sort of like what Stephen just said, like it doesn't matter the actual encoding. Like if you're approximately correct, okay, maybe that one was actually more worrying. But like if you're approximately correct, like for instance, I don't really care about this. Do you have this? Or do you have like this? Like sometimes I will desugar this to that because this is a constant number of edges and this is a constant number of edges. So for instance, stuff like that, like sort of like what we were talking about with the binding notation, which never came up again. Like people had a lot of questions about that. And then after the lecture, I kind of reflected on the fact that like, yeah, this is never going to come up again. This is almost like, this is conceptually interesting to get you thinking about it in the right way, but don't stress too much about the syntax. Okay. All right. Now let's talk about sequence functions. Any last questions on cost graphs? Cool. Quiz time. Came early. You'll never guess why this is the passcode. Also, fun fact, the reason why, okay, well, the real reason why I picked the title slide that I did, which was like some yellow and blue lines that are going like this, is because they're parallel. Yeah. you try asking a generative AI to come up with a picture for sequences. Okay, like you don't have a lot of options. Okay, I have to work in the abstract. All right. So let's talk about some sequence functions. Well, if you're a sequence enjoyer, name every sequence function ever. That would take a really long time. Okay, that would take like 3 hours. So I'm going to name some of the sequence functions and maybe tell you about some of the things they do. But it turns out for this class, you're only going to need like less than a third of the sequence functions, I feel like. So you'll be fine. Okay. So I don't have enough time to go through all of them with you, so I won't. But a lot of the sequence functions are derivable in terms of the others, meaning that in terms of getting you thinking about the cost model correctly, which is all I care about, okay? I care about you thinking about the cost way more than about the specific things they do. All I need to do is tell you about some core sequence operators, okay? And then you'll understand the whole library. So some interesting functions we'll be looking at are this tabulate thing, map, filter, reduce, and a few other things. So this reduce thing comes up again. And then I'll also talk a little bit about some other ones. And then for the rest of this lecture, I'm going to be making reference to things as if we're inside of seek. Okay, instead of writing seek.seek, I'll just write alpha seek. Instead of writing seek.map, I'll write map. Okay, there will be almost no discussion, I'm pretty sure, of like list.map. Okay, so don't get confused. It's called map in this lecture, but that's okay. We're in a self-contained unit, different namespace entirely. All right. Okay, let's talk first about this one called tabulate. Has anyone seen the list signature in the SMLJ website or whatever, the SML website, and then saw list.tabulate? Yeah, so this is that. But what tabulate does is given a function that tells you what element to produce for any integer, then we're just going to produce it for a given range from 0 to n. Not inclusive on the top bound as per usual, right? So in particular, tabulate fn gives me f0 through fn minus 1 as a sequence using this left angle, right angle bracket notation that we've been talking about. Okay, that's what tabulate does. And it exists for lists, but it's kind of rubbish because like the list one is you could do it recursively and it has a terrible parallel span, right? So we can do better than that. What was that? It's on the homework. Okay, never mind. It's on the homework, but it's a terrible span. Yeah. Let's do a not inclusive on this bound. Sorry. Yep. Thank you for catching that. Good one. Numbers are hard. Actually, I think numbers are some of the least interesting things in the world. I'll be open about this. Like numbers are so uninteresting, you have no idea. One time I had a job interview and they were like, can you make a bank account that gets N every single day and then decrements by K every day? And it was crazy. And it was the least interesting problem they could have possibly given me. And the crazy thing is that I did it in SML. So it was so boring. Anyways. No, not at all. This was Jane Street. It was the boringest question I've ever received in my life. I'm so glad I don't work there. I'm perfectly fine to say this on the recording. Like, I don't care. I'm so glad. You have no idea. Okay, anyways. Seek to tabulate fn x goes to xn is going to be this, right? 0 through n minus 1. All right. Yeah. Yeah, so map needs something to take in at first. You could think of this as a map on, this already. You could rederive it in terms of that, I guess, but like this is strictly more general because you can produce literally anything from just an index, and you don't need to take in like a previous element that was already there. So map and tabulate feel very similar though in this respect. And in fact, I think I am going to explicitly address this in like 2 slides. Okay, so the cost graph for tabulate, and this is the thing you should remember. Remember the picture, okay? This is what it's going to be. It's the parallel n-way composition of all of these calls to f on various indices. I do them all in parallel. Every single one of these operations is done at theoretically the same time. All right. So I can parallelize all of them. So that means that if I had a constant function f, seek.tabulate f of n is O of n work, because I have to visit each of these nodes, but O of 1 span. And that's pretty darn cool when our alternative we've been working with all semester has been O of n span, right? So this means that, again, like this kind of idea is if you are kind of building this dynamically, like you don't know how many elements are going to be in it. If you cons onto the front, n times, that's going to be O of n work, O of n span, sure. But if you know this ahead of time, then you can get the O of 1 span, but only if you know already how many elements are going to be in the sequence. Okay, so it's kind of this different use cases here. Okay. Okay. So this is much improved, and we, what happens under the hood, maybe you can think of. Still behind your abstraction is, we create a new sequence and then we just fill in the boxes, and each of the boxes can be filled in independently of each other. Okay, that's all that's happening. All right. Any questions on this? Cool. All right. As promised, one of the most interesting things about sequences is that we can do nth in constant time. So that means that if I do nth right here, I'm going to take in a sequence and a integer, and then my requires is going to be true because I'm also describing what happens if it's out of bounds. So I get back in alpha because it's the ith element of S unless it's too long or it's negative, in which case we're going to raise that exception range I talked about earlier. I don't actually know. Range technically takes in a string. I don't know what string it raises with. It doesn't really matter. Just don't do that. There's no reason for you to. Okay. That's not true. That's not true. But yeah. So raises range. And the cost graph just looks like this. One step. All we do is one thing. You can't parallelize it. If it's constant time, you have to do the work anyways. So this is going to be an itty bitty cost graph for nth. All right. And this is just generally what we're going to see for a few fundamental operations. But nth being a constant time is kind of the interesting thing. Similarly, I said we have length in O of one work in span, and the only reason why that's possible, okay, is the fact that we store the length of the sequence with the sequence. Okay, the sequence has its length inside of it, so we just go and query that really fast because that length will stay the same for the duration of that sequence's life. So length takes in a seq, gives us an int, and gives us this n. All right, and the cost graph looks the same, constant time. Okay, all right. I'm just moving on quickly from this because I don't think it's very interesting. And then finally, we have map. Well, not finally, but we have map, as we said earlier, which looks very similar to tabulate in the sense that like map f on this sequence, just evaluates the same length sequence where I apply f to each element, same as the list equivalent. But it has an identical cost graph to tabulate because actually we can define map in terms of tabulate. We don't need to have a separate map. In fact, on the inside, what the sequence library is going to do is instead of writing like, some homegrown map, it's going to use tabulate. Okay, that's what's going to happen. So I didn't need to show you this, but I could have told you it was the same, but I'll do it anyway. So for instance, map on a sequence could be implemented this way. Instead of doing like, anything else, I tabulate where at each index, I simply apply f to the nth element of the original sequence, right? So, like a picture, if I'm mapping this sequence right here, what I'm going to do right away is I'm going to tabulate. And what tabulate does is tabulate makes a new sequence of the same length. And then I say, at each index, what should I put in it? And what do I put? Well, I put f applied to whatever was here. And here I put in whatever f was applied to at that index, so on and so forth. This is what it looks like, right? But it turns out that I can access this in constant time. So that's the idea. Okay. So we can make this in the same cost profile using tabulate and nth, where we have this. And the reason why this cost graph is going to look a little bit different. So I would say this is the cost graph of that function I showed you just now, this function. And here's why, right? If I wanted to analyze the cost of that function I just showed you, well, I need to use the knowledge of tabulate. So in particular, we said what? We said tabulate fn I goes to f applied nth si. I think I always get this backwards, but whatever. Or n. Okay. So in order to analyze the cost of this, I just use the cost graph for tabulate, but this is now the question. What is the cost of this guy? So in order to produce a cost graph for tabulate, I need to produce a sub-cost graph for this function I gave it. So I need a cost graph for applying nth to something and then applying f to something. Well, remember, the cost graph for nth looks like this. And the cost graph for f, well, it's going to be the computation node of f. I don't actually know how much this costs. It's variable in f, okay? And what do? I string them together. So I get this. And this is my cost of my, let's say, f prime, the f prime that I use in the same cost graph I showed you earlier. I'm going to go back all the way. This one, we're going to substitute for these. Does that make sense for everyone? I know I'm using f twice here, but this is the cost graph that represents the cost of this function. Does that make sense for everyone? Yes. I think it's an argument to tabulate. Oh, sorry, to map? No, okay. Yeah, so, okay, yeah. Oh, did I leave the n unbounded? My bad, yeah. So you do use the length and then you'd have a constant. So let's go here, and then you would basically do this and then an additional edge here. Does that make sense? At the very beginning. Yeah. Sorry. Thank you for that. But also, like, if you wanted to think about the analysis of the graph, you could contract that if you wanted, if you thought it, because it's equivalent at the end of the day. But yeah, you could do it either way. Note that I've also contracted another graph edge here because I started running out of room on the slide. But like theoretically, you'd want 1 for the nth and then 1 for f. But I also just contracted it here because I didn't really care. So it's fine. Because you're sequentially composing this and then also sequentially composing just f. But I don't actually, if you weren't to do that, I don't think anyone would care. Okay. The point is that we have this cost graph and there's an extra thing on it for the nth we do. Is that clear to everyone? And the length. Cool. Okay. This is our cost graph for tabulate. And so there's just the key theme here is how do we think about the cost graph when we sort of compose these functions, when this guy has something. And it just means that we replace the old f node with whatever this cost graph is. Okay, that's a general theme. We'll see another example at the end of this class. Okay. So map, same cost. Okay, if I had a constant time function, I promise you constant time span. All right, same deal. All right. And this is basically exactly what I just said. All right. Okay. The next most interesting thing we can do is we can fold on a sequence. But folding, if you remember what folding means, right? Actually, let's do it out, shall we? So if I had a list of like elements, let's call it x1 through xn, like a list, okay? x2. Would someone like to tell me if I did fold L F on this, well, okay, also with Z, what would this be? Like, what would the expression be that this would be extensionally equivalent to? How do we typically write this? It's going to be a bunch of nested Fs. I'll give you a hint, okay? Well, like, what should I put here? Where this is the most xn? It's actually going to be x1. x1 comma z, and then here we go, right? Exactly. Yep, okay. So we do this, and if you get the point, we're going to eventually come out here and do f of x sub n, comma, da da da. Yeah? But computing this is really friggin' sequential, right? Because because f is general, I have no idea what this is unless I already know this, and so on and so forth, right? So I cannot compute this expression unless I know everything on the inside, which is like potentially n many things, okay? Which is very quickly a data dependency. I have a data dependency here. That's exactly what this is. So what we're going to find is that for folding on a sequence, if I were to do this, I'm giving you an analogy for why I shouldn't do this for this case. This is why I shouldn't fold like a list on a sequence, because we're going to have easily O of n span, at least, depending on what the function that I folded with it is. Okay, but I'm going to introduce that linear dependency, which is really bad. But we can do something a little bit better. All right, we can do something a little bit better. And this is going to be, and this is exactly everything I just said. How can we do this for a sequence? How can we fold on a sequence in a way where I get rid of this dependency and I no longer have to deal with O of n span? Well, we're not going to be able to get rid of it entirely, but let's change the problem statement. Let's do this thing where, there's kind of this idea of we can either, to do something better, we can either weaken the spec or we can strengthen the impl with the same spec. I briefly talked about this, but basically, like, if I want to make my function do cooler stuff, do more stuff, I can either, have less expectations for what it should do, which is, the easy way out. Okay, have less expectations. Or I can just put in some elbow grease and implement it in a nicer way. This is in a case of weaken the specification. Reduce is not going to be exactly the same specification. We're going to impose a constraint on the function f that's passed in. And I'll talk about this in a second, okay? So here's the idea for, I'm just setting you up for the future. Let's look at the concrete example. So let's suppose I had this collection of things. Actually, wait, so hold on, here's the point. If I were summing all the elements in the list, if I were summing n many things, should it have O of n span? And the question ends up being, no, it doesn't need to have O of n span. So, okay, here we go. That's the example I wanted. Suppose I have this list of numbers, all right, all of them through 8. If I wanted to add this, if you wanted to see me add this, and I'm running very low on chalk, I could do this, and I could make you watch me do this for the next little bit. I could, like this, basically. Or, well, well, yes, this like this. Okay, I could very well do this. All right, and in fact, if you look at the slides ahead, this is exactly what I'm going to do, but I'm not going to do it on the board. This is what it could look like. We march forward and we do it from left to right. This is what Mulligan does. This is what Fold does. How exhausting is that? Oh my God. My computer's doing it at the end of the day, but I'm exhausted by proxy by knowing my computer might do that. Okay, so like, let's not do that. Okay. Does anyone see a better solution here? Like, can we do something better than sequentially marching from left to right? What do you think? Merging? Was that? Okay, that's also true. That's the smartest thing. But I think, did I say pretend we're not privy to the there's a closed form, but pretend we're not actually privy to the closed form here, or the actual contents of the list. Yeah. Use commutativity. Not quite commutativity here. Yes, one of them. Yes. Make it parallel. Yeah. Okay. He already got the idea, which was reduced. But yes. Sure. Let's give the perspective a switch. What if instead we computed the sum of this guy, which is implicitly this big nested parens? What if instead we did this? Whoa. Not quite. Whoa. All right, this thing. What if we did that? Well then, surprise, surprise, this is going to admit a better span. All right, and in particular, it's going to look like this. Boom, boom. Small change, I put in the parens, but now everything is different. Okay, parentheses matter. All right, so in this case, what I can do is I can do each of these in parallel. So I do the 1 plus 2, the 3 plus 4, the 5 plus 6, and the 7 plus 8. All of these happen in parallel, as I kind of alluded to you, right? And so then we can do these in parallel, and it's going to turn out we only need to do 3 steps as opposed to 7. Okay, and it turns out that in a closed form way, okay, we're doing the logarithm of the number of operations we used to have to do. Okay, okay, and that works out very well for us here. But can we do this in general? And the answer, as you can tell, I'm alluding to, is going to be no, because let's just work through it. Okay. For lists, all we can do is this thing. We can only do this marching forward because we don't have access to this ability to look at like everything at the end. But for sequences, we can reparenthesize. Okay. But also, what if I wanted to do this? Let's try it. Let's parenthesize it. Let's do it. 1 minus 2 minus 3 minus 4. What do I get? I get minus 1 minus 1 equals 0. Does that seem right to everyone? Cool. Whip out your calculators. This isn't quite right. All right. Because what this is going to be is 1 minus, I don't want to write it out, but like 1 minus 2 is like what? What? I don't know what to say to that. I don't know what to say to that. Okay, so 1 minus 2. What was her name? Actually, don't say that. Don't say that. 1 minus. I was thinking of a way to make it funny. Okay, I'm getting heckled. 1 minus 2 minus 1 minus 3 minus 4 minus 4 minus 8. Right? Okay, I just did the math for you. This is minus 8, right? I think. But this was 0. Wrong result, right? So what happened here? If I wanted to march forward with fold, it's minus 10. I'm right. I'm wrong. You're right. All right. Yeah, whatever. Wait, is that not right either? Ah, shit.
You're starting your accumulator at 0. The one you're doing right now, you're starting at 1.
Ah, I see what happened. Sorry, my bad. Let's do this.
Okay.
Look at that. Minus 10. Crazy. Okay. Yeah, I didn't get a whole lot of sleep this week. Okay. So anyways, what we see here is that if we march forward, we're going to get minus 10 here with the 0 minus. And if we were to associate these in a certain way, this is not quite right for what we should do. We should have the 0 minus in front. But trust me that if we try to do the parentheses trick here, like 0 minus this also, it would still be 0, right? So like we got an issue here. All right. So what do we do instead? Well, let's not do that. What's the problem? What did I miss? What big honkin' math fact am I missing here? Associativity. Associativity is what I was missing. So also key fact. Well, if it's not the same, I don't really care. The point is that it's not minus 10 is my point. All right. Key fact for you. Addition is not the same as subtraction. All right. In particular, addition is associative, subtraction is not. So, okay, let's talk about this in general. So associativity, what happens is if I have a binary operation, like let's call it circle, was there a question? Yeah, okay. If I have some operation like this is my binary operation, okay? Or let's actually do X, all right? Y, circle Z, okay? And it's binary, so I have to choose a way to paren. I can do it this way, or I can do it this way, right? One of those two things is my interpretation. Associative means that both of these are the same thing. Okay, always. It means that if I have a list of these things and they're all separated by the same binary operation, I can put parens wherever I please and it'll be okay. All right, so as long as it's syntactically well formed. But I can put parens wherever. All right, as long as I don't permute the order. Permuting the order is not allowed. That's commutativity. Yeah. We'll still have a fold L for sequences. It's just that it will have a bad span. Yeah, but you can still do it with reduce, so long as you maintain this invariant. Okay, so you don't have to use fold. Reduce is more particular than fold, but fold is more general, right? Okay. But associativity is the real big deal here. Okay, so we can put the parens wherever, and that's basically what I'm just saying here. And reduce is going to make use of this idea. So let me roll back the clip. Okay, I showed you that with addition we have this associativity property, which means we can insert parens. Which means what? Which means we can do things in a different order in a parallel friendly way. So all I'm saying is that to do this reduce thing, which is going to do this pairing algorithm, much like I just showed you with the addition trace, all we're going to mandate is you need an associative f. Reduce requires an associative function f. All right. Here's our spec. Now, because it's associative, it actually constrains the type too. Okay, you can't do this and then output like a different type because you can't pair it up properly. Okay, but the point is that fixing an alpha, I'm going to have a function that takes in two alphas and produces an alpha. That's my associative function f, a base case, okay, and a sequence. And this is actually going to be equivalent to fold R given this Z given G with this reduce function, okay? I guess I motivated this with fold L, but it'll actually be equivalent to fold R. We keep this base case at the right, but the difference between what you saw earlier with reduce 1 is reduce 1 doesn't have this. But it requires that the sequence be non-empty. Because, for instance, okay, if I didn't give you a base case, what would you give me back on this, right? You wouldn't know. You couldn't possibly produce any arbitrary alpha for an alpha sequence if I told you I wanted you to reduce with this without a base case. Does that make sense for everyone? Yeah. So reduce 1 simply says, now you must have at least one element, but also I don't need to give the base case. That's the only reason why it's here. Okay. But reduce is going to mandate this total and associativity property of the function. All right. And it's implemented spiritually the same way I just showed you with addition. What it's going to do is it's going to pair up everything that it can, and then like a round robin, it's going to just make everything go pairing up again and again and again until we reach the end. And if you have kind of a conceptual notion of what that means, it means logarithmic span, right, for a constant function f. Yeah, actually, I don't really know what a round robin is. I said it because it felt semantically right. But I think it would be a bracket as well. Yeah, you're right. Not this kind of bracket. Oh yeah, you can get actually, this is like the last bag. This is like I need to buy more. This is the last 4 high chews. Do people want to like earn these last 3 high chews and the 4 high chews in the last like 20 minutes? I'll treat that as a challenge to you. Okay. So what's the cross graph look like? It's going to look like this guy. Boom. So what we do is we parallel n ways. And out of each of these guys, you can think of each of these blue dots as actually like the element at that index, okay? We take all of these elements and we just pair them up via our function g, and I actually left it out here, but z is chilling somewhere to the right, okay? And it doesn't need to be a perfect bracket. Like reduce kind of is smart and it knows how to pair things in a way that eventually will get to this case, okay? And you can think of it like it doesn't need to be a fair bracket. Not everyone needs to go through the same number of rounds, because it's going to be in the neighborhood of logarithmic, okay? Sort of like the red-black tree thing, okay? But does this make sense to everyone? I'm doing a bracket and I pair everyone up, all right? And if you're unlucky, this is gym class, maybe you don't get picked and you're Z at the end, but that's fine too, okay? You'll get there eventually. So that's reduce. And this is going to admit, if you count up everything, okay? Well, actually, can someone tell me why or what the worksheet for this should be in terms of calls to G? Strictly in terms of calls to G. How many calls to G are there? What do you think? in the neighborhood of n, right? Yeah. And let's work through why that is, right? So at this first level, there's going to be like what, n over 2, right? Roughly n over 2. And then each time we're going to, that's also true. Yeah. But also, that's a good point. But also another thing is like this is the same as the work span thing we've been seeing all semester, which is, well, not all semester, but like we're dividing by 2 each time, which means that when we sum them all up, it'll be the same as in the neighborhood as the biggest one. So n over 2, n over 4, n over 8, down to 1 or 2 or whatever. This sum is in the neighborhood of O of n. Okay, it's bounded by n. All right. So that's why we know this is still going to be work in O of n, but span is going to be logarithmic, right? Because I divide by 2 that many times. This is just a different presentation of the same kind of stuff you've been seeing all semester, which was like trees that are like dividing by 2 and splitting, or combining, right? All right. I guess like kind of reverse in a sense. And it might look scary, but again, this is just the divide and conquer algorithm. If you can kind of intuitively think about it, I'm not asking you to implement reduce. And it turns out like if your operation is associative, like it literally doesn't matter how the brackets happen. It just matters that like it'll be equivalent to doing the fold, just that it'll be faster to do. Okay. So just in terms of the spec, in terms of using reduce, just remember it's always equivalent to fold R here. Okay. That's all you need to remember. Okay. Okay. So I already gave you all this justification, but yeah, for addition, O of n work log n span. Not bad when addition on fold is O of n span. And remember, log is practically constant for all intents and purposes. So this is truly pretty good. Okay. That was the end of reduce. Any questions on that before I finish and go to filter? Okay. All right. I like filtering. Let's do filter. This is filter on sequences. It looks pretty much exactly the same, but instead of lists, we have seek. Okay. But how is it implemented? And you might naively think, if I asked you to come up with the cost bound right now, and probably I should have done that, you might think O of n work, O of 1 span. It's not going to be true. Why? It comes out to the same thing I told you at the beginning of lecture, which is just that the bad thing about sequences is it's kind of hard if you don't know how long your sequence is going to be a priori. Okay. If I have an arbitrary predicate P on a sequence, I have no idea until I actually go and do it how many things are going to be in the sequence. That means I can't magically, make my sequence of the perfect length and then put everything I want into it, right? I have to kind of use a little bit of communication to form this sequence. Okay. The actual implementation of filter relies on a kind of technique that you will learn in 15.2.10 if you take 15.2.10. So I will tell you the cost bound, but I will tell you how you can think about it, but it's not going to work exactly. Okay. So here's what we're going to do. Okay. The implementation is subtle. So I'm going to tell you it'll be O of n work and O of log n span. All right. That's what I'll tell you. And I'll also tell you that it's going to look something like this. Okay. This is going to be how you can think of the pseudocode. It's not actually implemented like this because this has the wrong work bound. Okay. But what you can intuitively, well, this is not actually what happens, but you can think of it as mapping to none or some, depending on if it satisfies P. Or actually, alternatively, actually better would have been to say it maps X maps to the empty sequence or the sequence containing X, depending on if it satisfies P. Okay. And then we bracket it out. We reduce with append. We append everything together. And if you think about it, if we do that, right, the only things in the resulting sequence should be stuff that satisfied P, right? Because we killed everything that didn't satisfy P. So that should make sense as to why it works. This is not what happens because this will actually have too bad of a work bound. I don't think I mentioned, but seek.append is like linear. Okay. So this is not going to work out. I believe the span will be like, bad. Like, n log n, I think. N log n. But this is why the span is log. Okay. This is the intuition for why the span is logarithmic. There's still like a kind of reducing thing going on, but for all intents and purposes, trust me, it has this working span. All right. Yeah, specifically because you're doing this reduce thing. You're doing this reduce thing, and append has an O of n or O of 1 span. If everything remained in the list, you'd still have to pair them up pairwise. And also it depends on the cost of your function f. So this is just the flavor for why the span is logarithmic is down to reduction, down to reduce, right? And that's all I'm going to tell you about it. Okay, take 15.2.10 for more. All right. Cool. Those are the main weird sequence functions in terms of their runtime. There's a lot of other sequence functions out there, but most of them do not actually matter in terms of their runtime because you can derive it in terms of others. There's a few I didn't tell you about, like append is linear, for instance. That's like something you should think about. You could rederive that in terms of tabulate too, actually. That's a good exercise. But your TAs will go over all of this with you in lab tomorrow. They're going to go more in depth onto all of the costs of each of these functions. Yeah. Reduce filter and length. Yeah. Yes, I believe that's correct. Yeah. Those functions, and then a few more might show up tomorrow. Okay. And that's all we're going to need to get going with programming with sequences. Okay. I'm sure the ideas are racing around your head now. But when we are dealing with bulk operations on data, that's where sequences shine. When I have to like map a bunch of stuff, what if I can map everything in parallel? What if I could filter logarithmically? What if I could reduce all of that data? It's really, really useful. So spreadsheets, for instance, are like a very functional idea, and they would benefit a lot from this over like lists. Okay, and I'll leave it to you why spreadsheets are a functional idea. Okay, any other questions on these sequence functions before I go to a motivating use case, and then finish off the lecture? Cool. Okay, y'all are full of no questions today. All right, and then some. So let's talk about if we wanted to sum everything in a 2D matrix. So you know, I'm sure you're familiar with the idea of like a 2D list, or well, I guess 2D matrices were, no, it's not. Matrices can be like multidimensional. But the point is like a 2D list, okay, like an array, like a matrix, okay, or a 2D array rather. All right, let's think about summing all of those entries. So what do I mean by that? I mean, if I have this m by n thing, so m here, n here, and I've got a bunch of friggin' entries everywhere here, okay? I want to take the sum of everything in here, produce the final sum, all right? And if you think about, you know, the work, okay, yeah, we got to do everything, right? We got to do m times n because I have to sum everything. I have to visit everything. But we don't need to be constrained if this were a list of lists, right? Think about a list of lists. So basically, what that means is that this will be a list, and then this will be a list, and so on and so forth. This will be a list. When I fold to do this, I would use a fold. On each of these inner lists, I can't go forward to here without having to visit here as well, okay? So my span is bottlenecked by this O of m still, all right? By the fact I have to visit all of these. And it's also bottlenecked by the fact I have to visit each list element individually, right? So bad span, right? But what if instead we had, I'm sure you can get the idea, but it's going to look like this. It's going to be a sequence of sequences, which is m by n in size again, okay? It's a sequence of length m, where each element in this sequence is a sequence of length n. Does that make sense? Does everyone see pictorially? Like if you put this here and there, it would like read as literal math, okay? I've just indented it slightly. So let's do some matrix, which is of type int, seek to int, right? I take in a 2D sequence of integers, all right? Here's how we can do it. It's just that code. What do? I define sum to be reduction via op plus with a base case of 0 on S. Then I map sum, and then I sum. How does that work? Let me give you a picture, all right? So this code here is going to be witnessed by this picture, right? If I have, for instance, this 2D array, this matrix, what I'm going to do is I'm going to go and I'm going to reduce across each entry. That is to say, each row, each inner sequence. So I pair them up in these parens. This is a concrete example, but it could be as long as you like. And I get this, right? And now I'm done with my map. I've now mapped sum across each row, and I get this. And then finally, I sum across each of these by using reduce again. And the benefits of reduce on 3 elements is pretty low, but you get the point that like this paren stuff would keep going. All right. That's the picture of what the code I just showed you is doing. Let's think about the cost, because the real challenge here with sequences is like less programming, more. Okay. Well, I mean, not to say there aren't interesting programming questions, but like analysis of why the thing you programmed has the right bound is the bigger deal. Okay. Here's what the cost graph looks like. Okay. And you should think about this because I basically stuck the cost graph for map and I joined it together with sum. Okay. I map where each of my entries here is sum of r sub I, where r sub I is the ith row, 1 index for whatever reason. Okay, I decided. Actually, I should do r sub n, whatever. The point is, or n of n many such n many such rows and I sum all of them. And then what do? I join all of them together via my sum operation yet again. Okay? Does everyone agree with me that this is what the cost graph approximately looks like? Cool. Well then, let's do it. So I have m calls, or sorry, I have m calls for an m. Oh wait, should this be m? Yes, it should be m. Sorry. Yeah. Each of these r sub i's is n in length, and then there should be m of them. My bad. And then we sum all of these. Okay. What's the cost of this though? So we're going to employ the same technique that I did earlier this lecture, where I take the cost of each of these and I substitute the purple nodes by the green nodes. I substitute the cost nodes for the computation nodes. So all of the sums in this graph are not made equal, right? In particular, these sums are not the same as this sum. Why? Because each of the inner sums are on the ith row, which has n elements, okay? Each of those inner r sub i's is n elements long, so it has, via reduction, via constant time addition, O of n work and O of log n span, right? That's what we said earlier. But the outer sum has a sequence that's m entries long, right? Because after I collect all these sums, this guy is still m long. Okay? So then when I reduce across this, my cost is now O of m work and O of log m span. So if I know, and I'm going to show you this, it's as simple as looking at the individual nodes and then summing them. So given that information, I can substitute for all the nodes. So let's do it. That's it. I look at the sums of r sub I, and I replace it by something which was O of n in work and O of log n in span, each of them. And there's m many of those. I didn't specify in the drawing, but there's m many of them. And then they feed into this sequential node that has O of m work and O of log m span. How many calls are there to this guy, this green node? M many, right? So okay, so let's do the work, right? So how many? So okay, what's my work then? What's my work? Mn plus O of m, so Mn, because n is not 0. Okay, the only time it would matter is if n was 0, but it'll be O of Mn work. I don't actually have. I don't feel the need to write this down anyways. Okay, O of Mn work. But what about the span? What's the longest path? What do I do? There's only like all these paths look the same. Well, log n plus log m. I have to do both. This is okay. So what happens here is that because these paths are connected by sequential composition, I have to do both. So my bound is going to be in terms of both. If n were small, it'd be in terms of m. If m were small, it'd be in terms of n. And in particular, like asymptotically, it's both. Okay, O of n log n plus O of log m. Does that answer your question? You can define the smaller one in terms of 2 times log. If m were really small, but the problem is that like when m and n are completely like varying, like they both might be huge, right? Yeah. Asymptotically, like when m and n are both unbounded, like we have to take and count both. Sure. Yeah. Sure. Okay. I'm going to write it as plus because I like that better. So yeah, O of m times O of n plus O of m, which is O of n m work. And then span longest path is the sum. Sure, the max, depending, but yeah, both can still grow, right? I see your point. Yeah, sure. And I guess that makes sense because also like, when we do when we do recurrences and we have like, or rather, when we have these span recurrences and we have like S of, rather, I'm thinking of the case where you do the max and then they're different, like W of F1, W of F2. Yeah, okay, I'm fine with that. Yeah, okay. Let's write it as plus though. Is anyone confused on this? So I think the main thing that's important here is just that we find the cost node, replace it, and then you can just go and add some of the nodes, find the longest path. That's the main idea here, okay? And this will get more complicated, especially when you are dealing with functions that are not necessarily constant time. So for instance, in this function here, the one that we wrote, this operation we pass to map is no longer constant time. So the main way that we deal with that is you can't just say, oh yeah, seek.map has work of O of n and span of O of 1. No, because that's assuming a constant time operation. So how we deal with these other kinds of nodes is that we just replace, which is akin to basically composition, like multiplying, basically. Okay, we multiply by n. All right, but the picture looks like this. All right, and that's summing the matrix. Okay, and then we could be cute about it and we could say this was it. But this will be helpful if our call to sum matrix was subservient to like a bigger computation. Like what if we mapped with sum matrix? All right, now you get this nested picture, right? You can visualize it on your own time. But yeah, we would have like more of these, right? But that's all. This is an extensible, it's a composable process. I can continue doing this however long I like. All right, and I didn't put pauses on this, but okay, that's fine. Sequences are useful, and I think there's three main reasons for why. So one, I'm showing you abstraction in the sense that I'm not showing you other things. I'm not showing you the implementation. You shouldn't have to think about the implementation. Think about the brackets. Think about the brackets and like a little bit think about the array. Well, the quotation marks array. All right, it's in the mascot suit. You don't know if it's an array or not, but like it probably is. Additionally, if you had something in your head where like, oh man, we're using these linked lists, functional programming can't do constant time access, you're wrong. You're wrong. All right. Without needing to compromise immutability. And I realized I didn't motivate that a whole bunch, but I motivated immutability a lot this semester. Okay, like immutability is better. We can keep immutability and also have the benefits of arrays. Okay. And then also I can think about span in a more nuanced way. All right. If you liked this lecture and if you liked this sequences homework, this is essentially all 210 is. This is 210 is this lecture like 13 times. All right. But they're not as nice to work with as lists. Lists are kind of the bread and butter of any functional programmer. But again, use the tools you have, use the tools you need. All right. We can make our own tools. Thank you. All right. Yeah, that's it. I finished 7 minutes early, but I don't really have much else to say unless people have questions. All right. Dismiss.